Hi, today I will give a talk about modeling collective emission in cavities by phase-based trajectories. This talk was designed for APS meeting, but since the APS meeting is already cancelled, I will give it online. Here is the outline of this talk. First, we start with standard theory of cavity QED. In cavity QED, people study quantum matter interacting with quantum photons in a confined geometry. So what forms these cavities? For example, a pair of mirrors or nanoparticles near a metal surface. These can form the cavities. The simplest model for cavity QED is the JC model, in which a single two-level system, electronic two-level system, is intact with a single photomode. Here is a figure for the JC model. The benefit of cavity QED is that firstly, with a cavity, it's relatively easy to form a strong light matter interaction so that one can study the spectrum splitting. Another benefit is that in cavities, the photonic local density of states are modified so that the Fermi-Golden rule rates and other physical quantities can be modified. Lastly, recently people find that by putting molecules in the cavities, the potential energy surface of molecules can be changed so that the so that cavity can serve as a catalyst to catalyze chemical reactions. Here in this topic, we study an electronic two-level system interacting with a multimode cavity. And here is the Hamiltonian. First line is the first term is n two-level systems. Second term is m photomodes, and the last line is the light matter interactions. How to solve it? Basically, for such a system, the computational cost should scale exponentially with the number of two-level systems. So basically, it is very hard to solve it classically. One can solve it if a quantum computer is already in hand. By contrast, we can also solve such a complicated Hamiltonian by sampling independent trajectories in Wegener phase space. This method scales linearly with the number of two-level systems so that it can be relatively easy to apply to a lot of two-level systems. The basic idea of how to map a cavity QED problem to phase space is as follows. For this approach, we call it the Miller-Stokes dynamics. In principle, for this dynamics, we first map all Hamiltonians for all operators in this Hamiltonian Cartesian operators. For example, this is the original Hamiltonian. For photomodes, the A-A, we map it to XMP, and this is relatively trivial. For photomodes, for two-level systems, we map them to two-level systems. We map the two-level system to A-A like this, so that we can write them as a linear combination of X and P as well. Here, K and L denotes different electronic ground state or excited state, and alpha is the index of different two-level systems. Here, we map each two-level system to two harmonic oscillators, so that we can write them in X and T relatively easily. Hence, we can, by using the Miller-Stokes mapping, we can map the original quantum Hamiltonian to a function of X and P, which is very similar to phase space dynamics. The next step is to write down the equation of motion in Wegener phase space. Here, rho W denotes the density of the phase space distribution. And if we ignore higher order terms, this equation of motion is nothing but classical Liouville equation. The higher order term in our scenarios is proportional to G0, so that ignoring this term is a good approximation in the recoupling limits. If we ignore this term, we get classical Liouville equation, and for classical Liouville equation, we can firstly express this rho W as a linear combination of different independent trajectories, so that each trajectory we can solve it classically by classical mechanics. The only difference compared with the classical dynamics is that the initial condition for X and P for different trajectory L is sampled with the zero-point energy and zero-point energies of photons and electrons. And this is the only difference. And one need to remember that the initial condition of both photons and electrons are sampled according to the zero-point distribution in these classical-like equations. Now, let's move to the advantages of this dynamics. The first advantage of this dynamics is that the MMST dynamics can provide us a very good intuitive interpretation of cavity QED. For example, according to DDC's quantum interpretation, they said when we have a QED system, it will have two sub-processes. One is called the radiative self-interaction, which means the small system fluctuates and polarizes the reservoir, which reacts back on the small system. This will result in if only the self-interaction is considered, it will lead to the breakdown of electronic ground state. By contrast, there is another process called vacuum fluctuations in QED, which means the reservoir fluctuates and interacts with the polarization induced in the small system. If vacuum fluctuation is considered only, it will lead to the spontaneous absorption, which is also not good. If both the self-interaction and vacuum fluctuations are considered together, it will lead to a stable electronic ground state. This is what we observed. And according to DDC's quantum interpretation, the self-interaction and vacuum fluctuation are both very important. They can have different results, and by considering both, we'll get a stable electronic ground state. And in our case, remember that we sample initial conditions of both photons and electrons, and we can find that sampling electronic zero-point energy means radiative self-interaction. Look at this figure. If we sample only the electronic zero-point energy, which means the blue line, when we plot the excited state population as a function of time, we find it goes down, which means if we only consider the electronic zero-point energy or self-interaction, then it will break down electronic ground state. This is exactly the same. By contrast, if we sample only photonic zero-point energy, we can say this is just vacuum fluctuations. And by doing this, which means the green line will go, the excited state population will go up, which means it will have spontaneous absorption. If we combine these sampling procedures, which means if we combine self-interaction plus vacuum fluctuations, we get a relatively good stable electronic ground state, which is the red line here. Hence, the sampling procedures in the MMST dynamics can have some physical meanings. Their physical meanings are radiative self-interaction and vacuum fluctuations, respectively. And this is very good. Apart from their intuitive interpretation, these MMST dynamics can also get very good prediction of collective emission when we have many two-level systems. First, let's do a simple test. If we only have a single two-level system starting in excited state, and when the system is excited, here the left-hand side is the electronic population as a function of time. The solid line is the excited state. The dashed line is the ground state. The black one is the quantum result, and the red one is the MMST result. As we can see, initially the excited state population decay exponentially, and then later the population was pumped up again, which is called the Poincare recurrence. On the right-hand side, we plot the E-field intensity dynamics as a function of the cavity position for different times. At 0 time, the bottom one, there is no EM field later, the EM field was generated. As time goes, the EM field just go out and then bounce back. At this moment, the EM field re-excites the two-level system, which corresponds to the Poincare recurrence. Later, the EM field emits again. As we can see from these two figures, MMC dynamics can give us very good prediction compared with QM when we have only a single two-level system in excited state. But this is not surprising because a single two-level system in a cavity can be easily propagated quantum mechanically. Now let's do something more challenging. Let's consider 101 two-level system in a cavity, and only the middle one is excited. The red one means the excited two-level system, and the blue one means the ground state two-level systems. When the separation, we call A, the separation A between different two-level systems is half of the wavelength of the emitted field, we can see the MMC result, the red line agrees with the QM result, the black line very well. And when we decrease the separation to a quarter of wavelength or 0, basically QM results agree with MMC result very well. But it's still not surprising because if only a single two-level system is excited, it's still very easy to study it in quantum mechanical way. Now let's do something more challenging. Let's consider this scenario when we have a lot of two-level systems excited and the separation between different two-level systems is just very small compared with the wavelengths of the emitted field. So we say basically the separation between different two-level systems is almost zero. For such a case, in QM theory, people can use Dick superradiance model to build n+1 quantum states called the bright states, so that it's also relatively easy to propagate and solve. And with MMST, we can get some result like this. Here, the part A is the average excited state population as a function of time. When we have one two-level system excited, the red line. When we have 7 two-level system excited, the green line. And when we have 35 two-level systems excited, the blue line. Here we can see the initial decay rate becomes larger and larger when we have more two-level systems. If we fit the initial decay rate as a function of two-level systems, number of two-level systems, we'll get such linear scaling from MMST dynamics, which agrees with Dick superradiance prediction. Moreover, if we do some trick of the population dynamics, say if we take the time derivative of the average excited state population as a function of t, so that now the y-axis is the time derivative of the excited state population, and the x-axis is still the time. We get something like this. The blue line is the result for 35 two-level systems. Let's say MMST dynamics will predict it will have a very big peak at some time. We call this time the delay time. So basically, MMST dynamics predict that at delay time, the derivative of the excited state population will have a peak, and then it will go to almost zero. Such a behavior can be predicted by a simple mean field model. But remember that in MMST dynamics, we average the result over many trajectories. If we zoom into different trajectories, we can find something bonus. Look at the right figure, where the bold blue line is just the original average result here in the left figure, are the same. And the thin color line is the dynamics for different individual trajectory. As we can see, for different trajectory, there is a different delay time, different peak here, which corresponds to a different delay time. If we do some statistics of the delay time for the MMST trajectories, we get the figure B, where y-axis is the delay time and x-axis is the number of two-level systems. and this is the error bar. As we can see, the QM result agrees with our MMC result very well. So that MMC result not only can give us some average population dynamics, which will recover some mean field results, but can also give us some quantum statistics from counting different trajectories. This can also agree with QM result. Actually, this is a very exciting result of MMC dynamics, because if we just propagate different trajectories, we can use it to mimic different times of experiments, and then we can get statistics from different trajectories. Another benefit of MMC dynamics is that with MMC dynamics, we can investigate more scenarios. Previously, we studied the two-level system separation is almost zero. However, we can also study the case when the two-level system separation is not zero, say, is a quarter of the wavelength. For such a scenario, when all two-level systems are excited, basically one cannot solve it quantum mechanically, because in this case now, because there is a separation between different two-level systems, the dark state is not zero. The dark state population will be important, and one need to consider the dark state population for all excited states, which is very time consuming. However, we can relatively easy to solve it with MMC dynamics. And from MMC dynamics, it gives us a result like this. Again, y-axis here for figure A is the average excited state population as a function of time. When we only have one two-level system, the black line is just initial exponential decay. When we have 7 two-level system, the red line, the decay lifetime, we can see the decay becomes slower in the later times. When we have 35 two-level system, green line, we can also see the delay time is even slower at the later stage. Now, if we do some fitting to get the lifetime of these slow decay rates as a function of number of two-level systems, we again get some linear scaling. Such a linear scaling agrees with some experimental finding. And so that this is another advantage of MMC dynamics. Such a behavior can relatively hard to be solved by evolving a full quantum Hamiltonian, because in this case, the dark state dynamics is also important. In conclusion, in this talk, we use MMC dynamics to study a simple cavity QED scenario when we have n two-level system coupled to a multimode cavity. And we find that MMC dynamics can give us an intuitive separation of the effects of radiative self-induction and vacuum fluctuations. Moreover, MMC dynamics can also predict excellent quantum dynamics when we model the collective emission of n two-level systems. Yeah, that is this talk.